right, thanks, Steve. So first thing I want to say about observables and their quantum gravity is how excited I am that it seems to be very much a subject which is in vogue these days. In this very workshop, we've had quite a few talks about it already. There was this interesting work that Will Donnelly presented. He's on with Steve Giddings about gravitational tails. Of course, there's the work by Schinker Stanford and the Chaos Collective about a commutator, an algebraic structure as a measure of chaos in quantum gravity. And of course, all the interesting discussions we had about recovering bulk from boundary by Ahmed, Shi, and Dan, and Joe, Eric, and Vladimir. So there's a lot of stuff going on. It all seems very interesting. So when Steve asked me to give this sort of overview talk, I wasn't at all sure what new things I could really add to it. And in the end, I decided that I will end up largely repeating various comments that I've made over the past few weeks of the program already. But some of those comments were made in private, so this is a chance for everyone to hear all the comments. I apologize. Some of them were made up here on this very stage, and I gave a short presentation a week and a half ago. But I will correct at least one thing I said wrong at the time, which is an important correction. Okay. So what are we trying to do in talking about observables in quantum gravity? Well, you know, once someone gives you the fundamental theory, whatever it is, usually it comes with some set of observables. The theory, that's part of defining what the theory is. I mean, we often think of observables in quantum mechanics or quantum field theory as defining the theory. And if you know the full set of observables in their algebra, at some level, quote, all you have to do is representation theory to find the set of states, and the rest of the theory follows. So if your theory is Tom's holographic spacetime, they're called Qs. If it's ADS-CFT, you think of sufficiently decorated Wilson loops as being the fundamental observables. They're called Ws. If you're a loop quantum gravity person, there are maybe triads and holonomies or something else. It doesn't really matter what the letters are. They're the fundamental observables of the theory. Now, I'd like to make some comments that are not tied necessarily to a particular theory. And the interesting discussion there is usually how do the fundamental observables, whatever they are, relate to the things that we're used to talking about in quantum field theory on a fixed background. How do you recover some measure of locality? All right. And most of us assume that this discussion, going from fundamental observables in the fundamental theory to local observables in quantum field theory, should run through the construction of diffeomorphism invariant observables in some low energy effective theory of quantum gravity. Okay? I guess effective field theory of gravity. Let's put it that way. Right. And this is a context in which you can have lengthy discussions because it's somewhat non-trivial to think about diffeomorphism invariant quantities which have some locality properties, yet it's concrete and well-defined, and we don't have to worry about what the fundamental theory is. It's not really so hard, of course. You can certainly write down many diffeomorphism invariant quantities that should be gauge invariant and observables in this low energy gravity theory. The action for your theory, for example, is one. The trick is to make them have some kind of locality.
Question?
Yes! Questions already. Wonderful.
To what extent is this problem solved in classical gravity?
I will tell you.
Great.
Okay, I will make that very clear. It is completely solved in classical gravity, and this has been known since at least 1962, if not earlier. But I'll explain that in due time. Okay. So there are age-old methods for I'm going to list some much-studied methods for writing down quantities that are actually diffeomorphism invariant and give some measure of locality. The simplest ones are, for example, one which is much used today is, of course, to introduce a boundary. Introduce a boundary, as in, for example, many people's favorite example of anti-de Sitter space. All right, where the fact that those diffeomorphisms that are gauge transformations are properly supported in the bulk and, in fact, do not act on the boundary due to the boundary conditions means that anything which lives at the boundary is essentially gauge invariant. That's an easy trick that we use in ADS-CFT to study a certain small set of somewhat localized observables. Of course, this trick doesn't help us if we want to study things that are deep in the bulk, at least not manifestly. Okay. Number two, age-old trick number two, is, of course, to fix a gauge. It allows you to find some quantity that has some notion of locality. If you fix a covariant gauge, it may propagate using hydraulic field equations, for example. And it gives anything which is any quantity which is well-defined in a completely gauge-fixed setting, of course, defines some gauge invariant notion if you work hard enough at it. So there's one thing you can do.
What about positivity of the metric? If you use a covariant gauge, most of the operators don't obey the rules of quantum mechanics.
Well, and of course, you notice that as I said, if you completely fix the gauge, any quantity defines a gauge invariant object. In most covariant gauges, there are residual gauge transformations that are not completely fixed. Of course, those problems are tied together.
But I don't think the operators, once you completely fix the gauge, are ever local.
I didn't say they were local. I said they have some measure of locality. They certainly don't satisfy microcausality. They have some notion of being attached to a space-time point. Thank you, Tom, for explaining why this is not anyone's favorite thing to do. Completely agree. I was trying to brush over that quickly. But yes, so this is one thing that you can do, and it has some unsavory characteristics. The quantities that you might call a scalar field at some space-time point and some time in some fixed gauge do not have the algebraic structure one wants to recover in local quantum field theory. They have non-local, may have effectively non-local interactions, and certainly their commutators will not vanish at all space-like separate intervals. Okay. All right. I mention this because, in some sense, it's completely general. Okay. Everything else that I'm going to describe, since if you fix a gauge completely, that will certainly define a gauge invariant operator. The other methods that I describe later, while they're sort of nicer and allow us to, well, they're nice in the sense they allow us to see the non-local properties explicitly. Many of them can be rewritten as an appropriate gauge fixing if you want to.
So, sorry, can I ask you a sort of dumb question?
Sure.
In which category do you put the literal observables that people have also been talking about at this workshop, things like CMB measurements? It's a finite time, so there's no boundary that's relevant.
Yeah.
We make measurements locally, and we have some idea statistically of what they mean.
The CMB measurements are an interesting. I mean, certainly not. They're not an example of.
They're not in
this
one,
case.
and in two. We often work in a fixed gauge, but we can shuffle among different gauges readily.
Of course we can.
Of course it works.
Of course we can.
So
are you going to add a third one, which is relational, or something?
is that,
Yeah, I'm going to add three. All the other categories would be called. Well, I'm sorry. I meant this in some sense. All of these methods use what we might call relational ideas.
Right.
To pick out the interesting places where we want to study the field theory. That term could be used here. You study things in relation to a boundary. It could be used here. You study things in relation to some structure that fixes a gauge.
Right.
And I can list more examples that come up. So
I'm just confused there because we don't really have to work in a particular gauge.
no. Well,
Well, there's a sharp thing. Well, there's a problem of time, as we know in cosmology. And the way that is solved is you study things on the reheating surface. And that's determined, of course, in terms of the value of the scalar.
Absolutely,
of the
yeah.
influence.
So it's relational
yeah.
in that sense.
Yeah.
But it's not. It's manifestly gauge invariant, I think.
Yeah.
yeah. I'll have another class that comes up which is closer to that one. I mean, the observables in cosmology are a little subtle to classify in terms of the framework, in terms of the examples I'm going to write down, because on the one hand, they tend to use a kind of clock field, the inflaton or such things, to fix the time hypersurface.
Right.
But then once you're on that surface, they don't tend to fix notions of individual points via rod fields or some analog. Instead, you assume you're near homogeneity and you Fourier transform and you measure things in terms of separations.
But you don't completely assume that. You test for it.
Of course you test for it.
And you find inhomogeneities that are
Yeah.
part of the point, and it's a statistical thing, so you have some, it's approximate in ways we understand, but it's perfectly gauge invariant. So,
Sure.
So this is not a new thing, of course.
So there, what you see, we look out, for example, our distance measures are basically angles, right, as seen by us as observers. So it depends on an intervening nearly classical spacetime, et cetera.
Right.
But
Of course.
I don't know that, let me go on with what I had to say here. You notice that I wrote down some much-studied methods. This is not an attempt to exhaustively classify anything or say that any other idea for constructing observables is necessarily a bad one. I'm just listing some common things that you might have seen done, and I'm going to make some comments. Okay.
But your list should include the observations that are made, right? So will you include Eva's things?
I just said I could hit some of them.
not the ones we care about?
I wasn't trying to give you a hard time at all. I think it's true that ADS-CFT has kind of made people forget some of the more simple-minded things that we can actually do. But keep going, I'm sorry.
Yeah, I don't have anything new to say about those observables, so I'm not going to comment.
Sure.
Okay? But they're fine.
Well, why wouldn't your answer to her question be that the CMB does count as being, the fields in a fixed gauge?
Well, I tried that too, it's a matter of semantics.
You don't have to fix a gauge to describe.
Go ahead, Tom.
Yeah, I think it's right there in the fixed gauge, but that we understand exactly how that gauge is fixed. Namely, we're assuming that the quantum field theory, which includes gravity in the usual analysis of the CMB, has a classical background, and we're close to a state where that classical background is there. Everything else is a small fluctuation, and then you use that classical background to define the coordinate system. And then things are gauge invariant because it's relational to all of the features of that classical background. So I think
But I mean,
it's different than what Don is doing, because Don is trying to think about operators that would be sort of universally defined without expanding around some classical background, I believe.
Not necessarily. So far I haven't done anything. I didn't mean to criticize this. As I said, almost any other scheme can be written as a fixed gauge if you work at it.
sorry, I'll say one more thing and then shut up. I'm confused by that fixed gauge thing just for the trivial reason that we understand how to change time reparameterizations and get the same answers out of the CMB. It's not...
Why is that?
Why is that confusing?
In any
Agreed.
fixed gauge, you can always invariantize it and then write down what the thing would be invariantly or in any other gauge you wanted to.
I didn't say that's the unique way to compute it. I said it can be computed as an object defined by some particular gauge fixing prescription.
There's a diff invariant way to state it. You look at the fluctuations when the scalar field reaches the reheating value.
Exactly. So you don't have to...
I apologize. I introduced this category for a pedagogical purpose that'll become clearer. I didn't mean to cause a great distraction by it. So I'll tell you the purpose now. What I meant here is, there's a long history of interesting people working hard to find, quote, good gauges that work for certain problems. Many of those gauges, as I will discuss, are related to well-known classes of manifestly diffeomorphous invariant observables. I was going at some point to comment that people that do numerical general relativity, of possible relevance because we're talking about gravity, often use a gauge called harmonic gauge. That particular gauge I have not seen much develop into a theory of truly gauge invariant or diffeomorphous invariant observables, and I think that would be an interesting thing for someone to do. That was why I mentioned this topic. But I'll just make that comment now, and we can move on.
May I
Especially, and I should say, I think that harmonic coordinates are especially, harmonic gauges or driven harmonic gauges are perhaps especially interesting in the anti-de Sitter context, where you can imagine driving them with boundary conditions. So I make that comment. Yes?
Yeah, regarding gauges in cosmology, that everything is so well understood, that's also the other statement, I believe. And one example is, for example, when you look at Nongaussianity, then sometimes you can work out things in one gauge and transform in another because this is non-linear.
Yeah.
Nongaussianity can be pure artifact of gauge transformation, and one has to be real careful of that. And people have not been careful in literature.
Could be. It's not my job to correct the entire literature today. So let me move on. Right. So, as we say, if we want to specify some location in a space-time, we may want to do it in some relational manner. And one of the ways, which has been much discussed already in this workshop, is to specify it using what are effectively some number of geodesics. This is particularly useful in a context like anti de Sitter, when you're really combining this idea with what I said up here. You would use the boundary to give yourself a fixed place from which to fire in geodesics, and maybe you could look where they cross, or you could go in a certain distance, so to speak. It's infinite in ADS, but we know how to regulate that, and talk about what happens as you go inside. This approach is interesting and was discussed a lot in this workshop because it has the property that, at least at this level of this effective theory, this amounts to, as was well explained by Will a couple weeks ago, having some kind of operator that corresponds to something you would think of as maybe a scalar field, and some kind of gravitational Wilson line attached to it. And so you know that this operator, of course, is not completely local. It has this kind of gravitational Wilson line that comes in from the boundary, but at least its non-locality is very confined to a tiny, tiny region. Okay? And so you can say that, you can imagine that, and so it follows that commutators with this kind of object will be exactly 0 in effective field theory, as long as the support of your second operator is space-like separated from this Wilson line and is M. Now, the comment that I wanted to make was the following. There was a discussion about using these in the anti de Sitter context. And so the idea there is you might want to run one of these in from the boundary. And it might be that if I draw you a picture of what's going on at one particular time in anti de Sitter space, let me call this the t equals 0 slice, the operator looks something like this. So we stick it in from the boundary. And then if we use this reasoning that I just suggested, bulk causality, to look at which operators on the boundary commute with this thing, we get the following picture. So let me draw a picture of, this is now the boundary of anti de Sitter space. Let me unwrap it, but I identify the two sides. Okay. There is a preferred point where we run in this geodesic from the edge, there. And of course, here the non-zero commutator expands out at the speed of light. But we also have something that lives here in the center of the space. And suppose that I had drawn this as a perfect circle with this point in the center, then bulk causality would tell us that there'd be some non-zero commutators on the boundary after the amount of time that passes, that is required for a light signal to travel from the center to the edge. And that is well known to be this time here, the time it takes for this light signal to go only partway around anti de Sitter space. Okay. So what's interesting is there's sort of two pieces to this non-zero commutator. There's the red piece and there's the blue piece. And I just wanted to make manifest that these pieces have, in a sense, nothing to do with each other. First of all, you see that the red piece does not causally seed the blue piece. There's plenty of the blue piece that arises just, so to speak, on its own, apparently from nothing. I also wanted to emphasize that these two pieces are different sizes. This blue piece is the obvious one that comes from not even worrying about this gravitational tail and just thinking about the commutator of scalar fields in bulk. Okay, so I will fix normalization and remind people who are not ADS-CFT, or explain to people who are not ADS-CFT experts what I am saying. We're talking about some action which is sort of the supergravity type, where I can think of all interactions as being gravitational strength. So I'll put a 1 over g out in front of my action, and then there'll be terms in here that look like derivatives of scalars, plus the Ricci curvature, plus et cetera, various kinetic terms. With this normalization, the commutator of two bulk scalars is, of course, of order 1 over h bar g. And loosely speaking, when ADS-CFT people talk about these things, they call this order 1 over n squared, correct, for certain examples of ADS-CFT. So my point is that in this notation, the blue region has a commutator of order 1 over n squared. In contrast, this red region came entirely from this gravitational Wilson line. Okay? Now, if you're working at the level of quantum field theory in a fixed semiclassical background, where gravity is not dynamical, then you don't need this thing. The field is already gauged there. So this tail is only required if you're doing things perturbatively, and as Will explained, when you go to the next order and you include essentially gravitational back reaction. So I wanted to emphasize that this tail has an extra factor of Newton's constant hiding in it. Okay? Or in standard ADS CFT speak, it means that this commutator here is of order 1 over n to the 4th, as long as the operator you stick in the middle is not particularly heavy. Okay? So I wanted to emphasize that these two things are really quite different. Even here, where it looks like the blue part might be causally seated by the red part, you see they're really not connected. Good.
Can you explain any current why h bar g goes down? If I just do the standard Poisson bracket thing, say to g bar goes up.
I think something's
he
a little
meant
confusing there
upstairs.
because normally g is small g.
Shoot, what did I do? What did I do? Typo, sorry. Okay,
Okay.
very good.
So it was not some deep things.
No. Small things. Very good. Thank you, everyone. All right. Right. And in contrast, of course, the area that I have not shaded is a place where the commutator is in some sense 0, where 0 really means to all orders in the semiclassical expansion. Okay? It's hard to imagine, it's certainly hard for me to imagine the result should be exactly 0. After all, in the full quantum theory of gravity, when Newton's constant is finite or n is finite, then we know that the different components of the gravitational field don't commute with each other, and that even if you decompose the metric into its conformal factor and its causal structure, even the causal structure has non-commuting components, so the causal structure presumably is not well defined at all. And so why should there be an exactly 0 commutator between the bulb and the boundary? All right. But anyway, 0 at least to all orders in the semiclassical expansion.
Don, could you just say again what defines the pink region?
The pink region is defined by working at this level of quantum fields in a fixed curve background, which is just anti-de Sitter space here, and ignoring gravitational back reaction completely, and saying what I'm modeling is a local operator here in the center, and I want to ask, when are there operators at the boundary that fail to commute with this operator?
That's the blue region.
That's the blue region.
Oh, I'm sorry. The pink region is the commutator, is the extra commutator you get with this gravitational tail.
So there are different ways to dress that, by the way.
This was one choice of dressing.
Yeah.
Right, so why doesn't the pink region meet the boundary at the, sorry.
Oh, why doesn't the pink region come over
close
here?
at the same place, yeah.
Let's consider the point on the boundary which is directly ahead of this line. Okay? The first signal it receives from any of these points will come from here.
Sure. But then immediately after that, you'll see a signal from a point on the Wilson line.
That's true. So I must have drawn something wrong. Thank you. Thank you. Indeed. So the correct answer is something.
It spreads out.
It spreads out. It goes like this? All right. It goes like that. Fair enough.
You're using bulk causality on that tail? Or you're using boundary causality?
I'm using bulk causality. Great. Thank you. Yeah, so this is the correct picture. So it spreads out this way. And indeed, all right, so even the pink region doesn't propagate causally. Thank you. Very good. All right. Anyway, my point was just to emphasize this picture and say that it would be nice to understand all of these transitions from any of the points of view that were advocated in discussions a week or so ago, either the code subspace picture of Ahmed, Shi, and Dan, or this gauge invariance perspective that Eric, Vlad, and Joe were explaining to us. So I'd like to understand those things. Okay. Very good. What do I want to say? Right. I wanted to amplify how much I would still like to understand about this structure that I have not yet understood from either of those two models by saying that much of the discussion to date about this structure in ADS-CFT has focused on the commutator of bulk operators like this with local operators in the boundary. But of course, it's also true in this picture that any non-local operator supported in this black region, like, for example, a Wilson loop, will also commute to all orders in the perturbation in the semiclassical expansion with the desired bulk operator. So that's something I'd like to understand as well. Okay. Right. In fact, I have this following small puzzle that I'm very confused about, which is this. So let's take, here I'm going to draw on the previous talk. So this is for the people who've been here the past couple of weeks. Let me draw on this code subspace model that she and Ahmed and Dan were explaining to us. So there was this idea that local operators, that as long as the state of the theory lived in an efficiently small subspace, that you could get exact commutivity of operators like this with local operators on the boundary. Okay. Now, what's interesting here is that if I take an operator at a later time and sort of evolve it back to this time slice, we know that we should get some commutator which is not exactly 0. Okay. And as Steve Schinker pointed out to me, the correct answer is that that commutator is of order 1 over n squared. Now, I can make myself happy with that idea by saying that I'm evolving the operator backwards for a time of sort of order 1, so it becomes more complicated, and it's got kind of order 1 complexity. And you folks argued there are various n squareds in the size of the subspace relative to the size of the full system. And maybe it makes sense that an operator with order 1 complexity has a non-zero commutator of order 1 over n squared. I can sort of make myself happy with those words. But then I get myself confused because if I look at operators that live in this region, okay, like these non-local Wilson loops, and now I just make them wiggle a little bit, if I tell myself that Wilson loops with order 1 complexity should behave like these operators where I evolve backwards, then I'm not so happy because I feel like operators at this time with only order 1 complexity should still commute exactly with these bulk operators. So I'm confused.
But that strongly assumes that you can localize this. So if the gravitational tail was more spread out, you would have a commutator, the pink region would be everywhere.
That's correct. But as they argued, I think convincingly, you can choose the gravitational tail to be well localized. And in any case, I'll explain another example in a moment where the gravitational tail is effectively not there at all at this level of analysis. So I wanted to mention this small puzzle. Okay. I don't understand how it works. I also don't understand how it would work in the gauge invariance point of view. So I remain confused. All right. So what else can one do? Well, as I mentioned a few weeks ago, there's a third approach to constructing observables that I've always had a certain preference for. This goes under various names. I don't know. We call it, let me call it, for lack of anything better, sorry, this is number 4, the use of intrinsic coordinates. Over the years, this has been given many names, things like, oh, it's very closely related to deparameterization, homology, but it's an example. All right. So, and this is an approach that I learned to love from Bryce DeWitt, who did work on these things back in the 60s and 50s, apparently following up on work by Artie Kovar and various ideas going back probably to Einstein. Okay. So what's the point? Well, the idea is that if you happen to have a collection of given d+1 scalar fields, where d is the space-time dimension, I'm going to call one of them phi, and I'll call the others z, then you can write down an observable, which effectively amounts to trying to use the z's as coordinates on the space-time, and then identifying the value of phi when the z's take some preferred value. Now, this, of course, is only useful if you have a state of the system where the z's have some significant gradient and can, in fact, be used reasonably well as coordinates. But when that is true, you can write down a quantity that is manifestly diffeomorphic phi z sub 0, which is just the integral over the space-time, integral over d dimensions, phi of x, some quantity f that you can think of as a smeared out delta function, which is non-zero and large, peaked around values of these things z when they're near these prescribed values z naught, like so. And then we need a Jacobian to make this thing a density so we can integrate it over space-time. Partial z alpha back to z beta. Great. Okay. So as I mentioned when I wrote this on the board a week and a half ago, at the level of classical physics, you can immediately show that assuming that you have a space-time or a solution where z is equal to z naught at exactly 1 point, assuming that's true, you can show that the Poisson brackets or the Peierls brackets or the commutators of these things in the classical theory satisfy exact microlocality. They vanish exactly at space-like separation. So this, in some sense, is the answer to Mark's question of how do you talk about observables and locality in classical GR, or it's one answer. You can write these things down, and in classical physics, we think that any generic solution has some gradients of scalars running through it, and you can use those to identify points, and then these things behave just like the observables of field.
Of course, I mean, in the classical theory, we don't need lots of extra scalar fields. I mean, we typically introduce coordinates any way we want.
I didn't say they were extra. They could be the components of the Riemann tensor, or certain scalar invariants made from the Riemann tensor.
No, but we don't do that. Right? You do general relativity calculations. You just introduce your favorite coordinates, and then you calculate gauge invariant quantities as your physically interesting quantity. I mean,
sure.
Well, Gary, we do that. And we use distance from the Earth, the angle from we use coordinate attached to material things we have around us in concrete relativistic measurements.
So let me make a specific statement. We can do many things, okay? If your goal is to end up here, okay, with objects in the classical theory that have an algebraic, say, Poisson bracket structure that reminds you of local quantum field theory and are local in the sense that their commutators vanish at space-like separations, the only way that I know how to do that is by doing this with local fields. And I'll just contrast that briefly for pedagogical purposes with what Carlo just said. Given some object, the Earth at some instant, given some event, the Earth at some instant of time, there are various non-local scalars you can define, like the distance from the Earth. Okay? If you use those kinds of things to define your relational observables, then you'll find that, of course, you won't find exact microlocality because, your observables depend on the metric between where your object is and the Earth. Okay, they're not exactly local quantities. So it depends what you want to do. If the goal is to reproduce the algebraic commutator structure of local quantum field theory, then I recommend this approach.
This is, only going to satisfy microcausality at leading order, I guess.
That's what I wanted to correct from last time. Okay. This actually satisfies microcausality to all orders in the semiclassical expansions I will now explain. I will now explain.
Okay.
Okay. Good.
These are classical fields, right?
I've written down this expression. Yes, let's think of them as classical. I want to think about this as, in fact, a quantum mechanical operator in some low-energy effective field theory.
Do you have to then say something about the state of the phi and z fields that they actually define in this coordinate system?
The state. It's got to be a. Let me say what I'm going to say. Okay? What I want to say.
I can't disagree with that.
What I want to say is that these things are satisfy exact microlocality to all orders in the semiclassical expansion. The semiclassical expansion is, of course, an expansion around some classical background. And so, yes, I wish to make this statement around classical backgrounds in which the z's are good coordinates.
Fine.
Great. Okay, so I've made my statement. All right. So now I'll give the argument. It's incredibly straightforward. How do you work in the semiclassical expansion? You take all of these, and I've now made these things quantum operators. Don't bother me about factor ordering. You choose an ordering you like, we'll make it work. Okay. How do you do the semiclassical expansion? You take each object here, the z's and the phi's, and you write z is z classical plus some quantum operator delta z. This is merely a definition of delta z. At that point, you start to tailor expand things. So here's the crucial point. Suppose you want to work to order n in the semiclassical expansion. Well, what you want to do then is take each of these complicated things, like this guy. I describe this as a smeared out delta function. Pick your favorite function of compact support, and I insist compact support. Okay? You take this thing, and to write it in the semiclassical expansion, well, you expand it. F of z minus z naught is f of z classical minus z naught plus the first derivative evaluated at z classical minus z naught times delta z, etc., etc., etc. And of course, as every mathematician knows, if f has compact support, meaning it exactly vanishes outside from compact set, then of course all of its derivatives do as well. So to any given order in the semiclassical expansion, this is just some polynomial times some classical function which vanishes outside some compact set. And now it's manifest that if I commute two of these, since there's a classical function there that localizes this integral in a compact set, if I do that with another one, it's got another compact set, it's manifest that if the two compact sets are space-like separated, they're not causally related in the classical background about which I'm expanding, then the commutator is 0. Proof complete. Okay. So it's just true that to all orders in the semiclassical expansion, these things satisfy exact microlocality, as long as we can talk about a classical background in which these z's are good coordinates. That may or may not be a good assumption that I will revisit in a moment.
So what about the intuition that these things should have excitations? Oh, I think I asked you this last time. Okay, so they have zero energy excitations.
These are zero energy objects. Actually, there's an order of limits issue here. Okay? If it is really true that the z's are good coordinates over the entirety of your classical background, even out to the boundary, then that certainly sounds like you've probably imposed some boundary conditions that break time translation invariance because you have a good clock out there. So, in fact, there's a question about what notion of energy is conserved in that theory. But I will return to that later. In fact, what I really want to do, as you may recall from last time, is modify this, is sort of combine this definition, or this approach, with something like this. I want to use this to give a very rough local notion of localization, and then I want to use this to refine. Yeah, Tom.
So, if I quantize GR in any positive metric gauge, there is in the Lagrangian all kinds of non-local stuff. Okay. Positive metric gauge. Okay.
Yes. Yes.
Now, what you're claiming is that you can give me explicit examples where you've constructed these observables, and to all orders in the loop expansion that never shows up in the commutator of these guys. That's what you gave us this argument, which I have to admit I can't poke a hole in. Have you done such a computation?
No.
Okay. I have to admit I'm skeptical.
Why should it be different? Before I get to the next question, why should it be different than with any other local field theory?
Because the Lagrangian is not local. So these things, at the end of the day, once I've picked a fixed positive metric gauge, these things are going to be built up out of fields which don't have local commutators whatsoever.
Yep.
And so you're claiming that you've constructed some objects which automatically, to all orders in perturbation theory, are going to have all those non-localities cancel. And if you say you can do it, and in a minute I will say to you, but wait a minute, these fields that you've defined are polynomial functions of arbitrary high order of local fields, and they introduce new divergences at each order in perturbation theory, and you have to prove to me that it's certainly not true that for any choice of the infinite number of unknown constants that you introduce as you go up in the loop expansion, that these things will be local. So you have to prove to me there's a renormalization scheme in which that kind of nice sounding argument really works. I don't think it's absolutely trivial that this is true to all orders in the semiclassical expansion. It's not a well-defined expansion without adding an infinite number of counter terms, and these operators add more infinities of counter terms. Your statement can't possibly be true until you've fixed all those counter terms in a special way.
Well, I'd love to have a longer discussion about this. I admit I'm not the world's expert on things like effective field theory, but I don't see why this is different than the kind of divergences that are discussed in every treatment of effective field theory.
Well,
because
for one
in
thing,
every
because
effective
this is
field
not
theory
a,
besides GR, we know exactly what local gauge invariant observables are.
And it works.
And yes, but we have things that are naively local, and you just see without doing any calculation that none of the non-localities in a physical gauge show up in those operators.
I guess, well, like I said, we can discuss this later, but the commutator, as a matter of fundamental principles of quantum field theory and quantum mechanics, can be defined in terms of basically advanced and retarded Green's functions. And so as long as the equations of motion are causal and your sources have a manifest locality about them, I don't see how there can be a problem.
Well, his issue was renormalization, and he's saying that how do you know that the renormalization doesn't introduce some kind of non-locality? And I echo that. That's a composite operator, right?
Sure, but at any finite order, it's a polynomial composite operator.
That's right, and in every finite order, it's going to get a new divergence associated with it. And it's absolutely clear that your statement about local commutivity will not be true for every choice of those finite renormalization constants that you need to define this operator order by order in perturbation.
I disagree with you.
It's absolutely clear.
It may be a question of which infinite constants we're talking about.
Because otherwise you're saying that associated with every one of these operators, there's an infinite number of operators. That any choice of the renormalization constants that it requires to define this thing in actual field theory will still satisfy these rules. And that I do not believe.
What I think I said is that at any finite order in perturbation theory, there's a large number of such things.
No. Give some fixed formula with a fixed f and all of that. For each choice, you will find that in order to define what you actually mean by that operator, you have to add in each order of perturbation theory more and more unknown constants.
I agree.
Okay. You are claiming either that you know how to choose those constants so that this classical statement of microcausality will remain true order by order in perturbation theory, or you're claiming that it's true for every value of the choice of finite renormalization constant.
Yeah, I think if you do things
so that would mean that mysteriously in quantum mechanics, for every operator like this you can write down, there are an infinite number of other operators that work to all orders in perturbation theory.
Yeah, okay, I can live with that statement. Fine.
I'd be willing to bet you a large sum of money. The calculation that will not occur for every value of the renormalization.
Okay. Well, let's
record that.
We'll take a few more comments and then we'll shelve the discussion. So Bianca's been wanting to say something for a while.
So I have a question too. So how do you define causality?
I just defined it. I'm doing an expansion around a background classical spacetime.
So you claim it's around this background classical spacetime.
Yes.
But then if you integrate out metric fluctuations, I don't really.
The statement, which you may be in Tom's camp of not believing, is that if you work in the semiclassical expansion around some given classical spacetime, which has a well-defined causal structure, then to all orders in that expansion, which of course is presumably only an asymptotic expansion. I claim nothing about convergence or any such thing. Okay, it will be true that these things have vanishing commutator when their supports are space-like separated. That's the claim.
Okay.
The claim is well defined. You may not. I've given a formal argument for it.
The problem
claim
is
is
what
fine.
is the answer to a given question, and I completely, what is the answer to a given question? I completely agree that you will face the non-standard problem when it comes to normalization, because you will have to admit non-local counterterms. And that is
I don't understand why the counterterms are more non-local when I talk about this than anything else. This is, after all, is by construction.
Theory, integration theory offer counterterms are local.
Counterterms are local. Exactly. So what's different here? This operator is non-local, but it's explicitly the integral of a local density. So what I want to do is renormalization of local composite operators and then integrate them.
That's not the issue, Don. Okay. The issue is that if I do this computation in a physical gauge, the expression that you will get for this will involve a whole bunch of divergent graphs which have non-local commutators, okay? And you have to show that you can define the infinite parts. These are not even, we're not just talking about the counterterms that you need to remove the infinities from general relativity. These operators have additional non-renormalizability in them. They're like unitary gauge operators in ordinary Yang-Mills theory. And defining what they mean as local operators is extremely complicated, even in the Yang-Mills case. There we have, because of the fact that the theory is renormalizable and we know how to go back and forth between unitary and non-unitary gauges, we have actual proofs which are long and hard, and if you want to dot the I's in them, they involve, someone like a Tuft working out before you believe that it's been done correctly. And it's not something that is manifestly correct here, and I simply can't believe that it's manifestly correct for every choice of the counterterms. That would seem like much more than the classical theory has. You'd have a whole set, a quantum ambiguity of infinite scope in each of your classical local observables.
Well, I disagree with you. The classical theory has a large number of these as well.
But for each choice, because the time for cookies is approaching.
It's true. It's an interesting question. I have to admit, I have a feeling that if we look back at some of DeWitt's work from the 50s and 60s, many of these questions are actually addressed on a course of modern language. But what Bryce would have told you to do is to use the fact that this is a gauge-fixed observable. It's equivalent to just working in a gauge where you fix the z's to be your coordinates. That defines a certain gauge, you can calculate it. And, he was certainly a fan of saying that the Green's functions in that gauge are all causal. That may not be quite the same as all the counterterms we're talking about. But I think you'll find that it simplifies tremendously.
So in ordinary Yang-Mills theory, these are, what you just said is like going to the unitary gauge for the Higgs field. And what you find in that gauge is that the Green's functions of the quantum fields are ill-defined. Order by order in perturbation theory, you need to add new counterterms to them. And there's a whole rigmarole that proves that certain calculations you do don't depend on all of those counterterms, including the S matrix, which is the thing you're mostly interested in. So, it's a highly non-trivial proof that relies on the fact that there is another renormalizable gauge where you can control all of the divergences in a manifestly covariant and local way, and just has this problem of negative metric, and so you use that gauge to define the quantities, and you use the fact that you can transform order by order into the unitary gauge to prove that those manifestly local finite quantities actually satisfy the axioms of unitarity. Okay, I'm sorry for speaking so much, but I mean, this is something that is well known in ordinary field theory, and you seem to be just, disregarding the technicalities in a way that just doesn't seem right.
This is a good discussion. But we should let Don move on, and then we should continue.
I propose this as a research program for someone to check. All right. Let's see. What else do I have to say here? Right. My point of saying this was that I do believe the statement that these things are microlocal to all orders in a semiclassical expansion. And so that suggests that one can indeed do better than this picture. Okay. I'll stop there. The question is how much better? All right. So as I was saying a moment ago, I'm pretty happy with these observables if you can work in a semiclassical expansion around some background where these z's actually define good coordinates. But that's not always the case. There can often be what I'm going to call infrared issues to deal with. Okay. So what kind of infrared issues might there be? Well, okay, problem number one is it might be the case that these fields just never take the value you want. This point doesn't exist, in which case the observables become trivial. Okay, that could be a serious problem. Right. Another problem that can arise are things that I'll call recurrences. Okay. So the trick here is that this becomes a diffeomorphism invariant quantity because you integrate it over all space. That means you can integrate over all. And if you have a system that is in any way finite, has a finite number of degrees of freedom, things tend to repeat themselves after a long time. In particular, it's interesting to talk about this anti-de Sitter case, and finite energy. It's a finite density of states, and at the end you get replication after a long time. So that's a problem, and it will lead to an infrared divergence if you try to calculate this. You just get the z field will come back to this desired value of z0 many times, and each time it gives a contribution. All right. But what I wanted to emphasize is that, in general, in a quantum mechanical system, recurrences are things that occur on a time scale controlled by the density of states. And so this is a problem associated with long times, roughly 1 over the density of states. Which, in the anti-de Sitter case, I might characterize as the anti-de Sitter scale times e to the minus the entropy, whatever the entropy happens to be at that energy. So my comment here is that...
Where are the minus signs in that?
There's a minus sign there. That's a tilde. This doesn't matter.
The density of states is e to the minus.
Oh, phooey. Thank you. All right. Sorry, e to the plus s. So if you have a system with a lot of entropy, these times can be, quite long. This could be considered a minor problem in that regard.
What is it that's recurring?
Everything. In this case, what's really recurring is these z fields you're trying to use as coordinates. You're interested in the places in the space-time where they take a certain set of values, and they will return to those values many times.
That sounds like that should be more frequent than the e to the s time scale if you're just thinking about those z fields.
It depends on the context. So let me give you an example. Okay? It may be. I think in principle, this is the only fundamental bound. Okay? There are certainly contexts where the z's live in some integral sector by themselves and they repeat themselves fairly quickly. All right. But as an example, we often like to talk about black holes as objects with lots of entropy. Okay? So imagine that you have your space-time and there's a black hole sitting in the middle. And I happen to have chosen a configuration or a classical solution where at some time the black hole spits out a coordinate grid of z fields, and then the grid field falls back in. Okay? So that's an example where the coordinate grid only arises at intermediate times and disappears in the far past and far future. And it is only the fact that many of us believe that black holes have a finite density of states that would lead you to think this thing recurs at all. So in this case, the recurrence is indeed tied to the density of states. Yeah?
Yeah. A bit confused. I mean, is it only some subset coordinate system that you're allowing yourself by saying they should be some physical fields which are based on physical equations of motion or something like that? Or otherwise, what would you can always specify a coordinate system that doesn't.
So these are supposed to be local scalar fields in the sense that they're local functions of things that define a local action. So they could
But
be.
are they obeying some equations of motion?
Well, let me say it this way. One of them might be the Kretschmann scalar. Okay. I'll let you answer your own question based on that example.
But still, the coordinate system itself is somehow a larger set of objects. I mean, the set of a set of all coordinate systems is then a larger set than a set of these fields.
I don't quite understand the question. If I'm in four-dimensional space-time, I could choose to work with 4 invariants built from the Riemann tensor in different ways.
So I agree that those particular objects might not give you enough freedom to not recur and so forth.
Yeah.
But you can still put a coordinate system on the space-time that does not recur.
You certainly can put a coordinate system on the space-time that does not recur.
So such coordinate systems, you're saying, are not. There are some coordinate systems which are not specifiable by the set of scalar fields.
In some solutions.
Okay.
Absolutely. Yep. Oh, yes. Very good.
I think Jim has a question.
Jim.
I understand that you're going to construct these fields out of some geometrical quantities.
Yeah.
But why should the wave function of the universe be such as to set up a coordinate system?
It doesn't. I mean, as was just emphasized, and as I think I mentioned before, this only works in particular states of the system.
Okay. Very special. You think those states are very special?
Well, I think they're clearly special in some sense, or at least with our normal kind of reasoning, they're clearly special. Let me just say it this way. We typically say that if you're at fixed energy, let's say in the ADS context where I can make this chart, that the typical state is characterized by the maximum entropy in the system, which is, say, a Schwarzschild black hole with basically just, Hartle-Hawking state outside. That state does not contain one of these manifest coordinate grids in any simple way. Now, I could say it a little bit differently. Okay, if you wait this long in such a state, it will do all kinds of crazy things.
Including setting up a coordinate system.
I think so. Right? So
if we wait long enough, right?
Well, so what I think is true is that generic states do not give you well-defined coordinate systems of this kind over most of the spacetime. They may give it to you in some small region. Great.
Thank you.
You're welcome. But what I want to emphasize is I think that these observables are nevertheless very interesting ones to discuss when we're getting to these fundamental questions about what's the causal structure, how does the bulk arise from some dual gauge theory, because there do seem to be at least examples of classical backgrounds where the commutator of a bulk operator of this kind can be made very, very small with boundary operators at the same time.
I agree with that statement.
Great. Yep. So again, it's a question of finding the right tool for the right problem. Yeah, right.
This is super naive, but if you added one more parameter, an integer which counted these recurrences, then you would get rid of the recurrence problem. Right?
Yeah, the question is how to do that in a useful way. So remember, good. Here the goal, whether I achieved it or not, was to reproduce, micro-locality to all orders of the semiclassical expansion. I will again mention that in order to do that, even at my formal level, it was a requirement that these be really what I would call local scalars. Okay? So, the same logic suggests that in order to enact your solution, one needs a local integer n that counts the recurrences. I think by definition that doesn't exist. Okay. So what one must necessarily do then is to somehow marry this scheme to something that involves some non-local relational quantity. Something like the idea of running NGDs from the boundary, some other kind of gauge fixing, something is the idea, maybe harmonic coordinates, something truly non-local, which in this ADX context would be tied to the boundary that localizes you within a recurrence type region, preferably parametrically smaller, but something fairly long, and then you could use this to control the fine structure. Okay. So the suggestion is that we should be able to make some observable by marrying these two things, and we should be able to estimate how small these commutators really are over most of them. Okay. Very good. Very good. All right. I guess I just wanted to mention quickly, before cookies, problem number 3. Problem number 3 is also an infrared problem. Instead of just recurrences in the expectation value, there can also be problems associated with the fluctuations in these observables. Okay. But this problem, it turns out, just as a way of heading off potential questions, is not a problem in asymptotically Minkowski space, and I don't think it's a problem in asymptotically ADS space, but it's a problem in things like de Sitter space. Okay. So how does this go? Well, the idea is that we're interested in studying fluctuations of these operators. That's a 2-point function. So let's look at the expectation value of 2 of these guys. Okay? They are both, by construction, integrals over the entire spacetime. So if I write these as 2 integrals, x, d, y, over some 2-point function, whatever it is, if you happen to have a non-compact spacetime, which is, for example, and you have a state which is maximally symmetric, so that this only depends on the relative separation of the 2 points and does not depend on the exact, on what you might call the center of mass degree of freedom, then of course when you integrate this, you're going to find that there's a volume divergence, first with the volume of space-time, coming from integrating over the center of mass. Okay? Even if the expectation value of either operator by itself was finite. Basically, the 1-point functions are easy to control by simply requiring the 1-point functions to vanish in the vacuum by some sort of normal order description or subtraction. But having done that, you no longer have the freedom to control the 2-point function. You get these divergences. Okay.
What is the space-length separated?
It's a 2-point function. It's not a commutator. There's no reason to let it vanish. Although in this, yeah. Exactly. All right, so there's some coefficient here times the volume of space-time. And if you look at this in the de Sitter context, so in Minkowski and ADS, this coefficient here vanishes because the energies are positive. So it's this same as this averaging argument that Tom was talking about last week. The 2-point function is a positive frequency function. In Minkowski and ADS, if you integrate that over the space-time, it has no omega equals 0 component. Okay, so you get 0. On the other hand, in de Sitter space, there's no positivity in the 2-point function because you're probably in a which we think of as a thermal background. You're in the bunch Davy section. And so in the de Sitter case, you find that there's a coefficient here which depends on the temperature. It's not zero. So, well, one has to...
Surely that's going to depend upon what operators you're looking at, right? I mean,
the detailed coefficient depends on the operator, but as long as these are, quote, the same field, as long as it's the same phi, then you get something non-zero. I mean, the basic contribution is just take the 2-point function of the...
Why wouldn't you get something non-zero in Minkowski space, too?
Energy conservation and positivity of the energy. So again, in Minkowski space, the argument is that this is a positive frequency function. And so if you integrate it, you're picking out, in Fourier space, an omega equals 0 component. But a positive frequency function has no omega equals 0 component. Let's talk about a massive scalar field just for convenience. We'll deal with the massless case later.
How do I know it's... So positive because it's the same field, right? And
Yeah,
it's information.
let me be explicit. I really meant when I wrote down here, this is a Whiteman function. So yes, well, all Whiteman functions are positive frequency. The negative frequency parts annihilate the Minkowski vacuum. It's all there is to it.
Forward 2.
What's that?
That's right.
And the same is true in anti-de Sitter space. And the point, of course, is that you could have used any state you like, but this is an infrared divergence. So it's only infinite because you're dealing with the parts of space-time that are infinitely far away. And all good states approach the Minkowski vacuum at infinity, or approach the anti-de Sitter vacuum as you get close to the boundary.
But you're just inventing this coordinate system. I mean, why should the thing have any particular properties in your invented coordinate system? I'm getting kind of lost in all the...
I didn't use any particular coordinate system.
No, this phi in your relational and your intrinsic coordinates has just been, the z points are just invented out of whole cloth, right? They're just scalars, there's some field.
Richard, just think of it as I've got my classical solution. Yes. With whatever coordinates you like. Let's use the ones that are simplest, okay, the ones adapted to symmetries. And then all I'm doing is writing down the integral of some complicated local operator, okay? And all I have here is the 2-point function of that local operator in the coordinates that you like adapted to your symmetries.
But what you really mean there is delta z at x and delta z at 1, right?
No, what I meant here was that integrand stuck in here evaluated at x, and that integrand stuck in here evaluated at 1. I was trying to save myself some writing.
Okay, so I can use the original perturbative
coordinate system.
Coordinate system.
Absolutely. Absolutely. Okay. So there's this interesting infrared divergence, and it's a question of what to do about it if you'd like to use these observables in, for example, de Sitter space. De Sitter space, at least global de Sitter space, is an interesting concept to think about because it has no boundary. So you can't rescue yourself by using a prescription like this.
Wait, what, you can still shoot then, like JB16?
Well, the boundary in de Sitter space is very different from the boundary of anti-de Sitter space. Diffeomorphisms are still active in full gauge transformations here on the boundary. So you can't save yourself that way. You have to do something else. Okay. All right. Now, in the semiclassical expansion, all you have to do...
Sorry, just so I understand, if it decays, that problem goes away?
Yes.
Yeah.
Absolutely.
Right.
Yep. So one way out is just to have the Sitter space decay. Not a problem. Yeah, you have to have it do something in the future and the past, but but basically if it's Sitter isn't stable, the problem goes away. Right. But this problem, it's a problem that arises at some given order, at leading order in the semiclassical expansion. So, this term can be large, okay, over just sort of polynomially large volumes of de Sitter space. So this term can, in principle, give you trouble, I think, over regions of space-time where you might... So even if you believe that there's a landscape and de Sitter space will always decay into flat space in the far future, in most landscape scenarios, that takes a long time to happen. And this quantity can still give you a large term that I think will bother you on timescales short compared to that. In fact, Ben and his friends have made this argument, have done the calculations for me in various contexts, and I'll explain when I just give you a new term here. Right? The reason this is a problem, the reason this divergence arises, is because, if you like, there are fluctuations that materialize for you a coordinate system in which these z's happen to be close to some value z naught. Okay? That's some sort of and think of that as a macroscopically coherent object, at least macroscopically coherent enough that it will be used as coordinates here. You'll see that that's very, very much like these classic discussions of Boltzmann branes and so forth. And so the paper that Ben and his friends wrote where they worry about Boltzmann branes arising and dominating things long before a universe might decay via some string theoretic decay to flat space, that's the same calculation, at least as far as order of magnitude estimates go. So you'd like to fix this up at a shorter time scale. And I'm going to close by saying that Steve Giddings and I wrote a paper some time ago where we had a suggestion for how to fix this up, that it'd be great again if someone could work out some details. Here's the basic idea. So how can it be that a two-point function diverges when the one-point functions are finite? It's kind of a funny thing, right? Because what's a two-point function? A two-point function is something that has, I'll put in a state. Here's these operators, phi z1, phi z2. I could insert a complete set of states in the middle. Probably if I write this here, no one can see it. But I'm going to insert an infinite set of states, a complete set of states, to write the two-point function in terms of one-point functions. If all the one-point functions, even their off-diagonal parts, are finite, okay, which they should be, the only way the two-point function can be divergent is if you get contributions from an infinite set of intermediate states. Okay? So the natural solution is to truncate these operators by, at the level of effective field theory, projecting them into some subspace which is finite dimensional and small.
Sorry, can I ask a maybe related question?
Yes.
Is this problem something that a single observer in one of these trajectories that does decay, is it a problem for an individual observer? That depends on how well you want your observer to live. Okay? It's only a problem if the observer samples a very large region of space-time. So that means you're talking about one observer. It's only a problem for observers that live a very long amount of time. You mean in units of the de Sitter radius? Or yes, in units of the de Sitter radius. Okay. So I suspect that from this point of view, okay, if you're worried about what one observer sees, I've actually forgotten, and maybe you guys had an answer to work out this calculation, but it may well be that if you're worried about what one observer sees, this is in fact not a problem before you expect the decay to happen. I'm thinking of it as a problem from this more local perspective. Okay. So anyway, here was a suggestion of how to proceed. This is a general formal suggestion, but I think that you could adapt this to the kind of framework that you're thinking of, Eva. You could decide that only those states in effective field theory, okay, are important which are mostly vacuum. Well, let's see. I have to say this.
You want to do this in global de Sitter? Is that roughly the idea?
Yeah, when it's in global de Sitter. Anyway, let me just say that the idea is that that we should be able to choose large but finite dimensional spaces of states that would allow us to build up an operator algebra that approximates that of local quantum field theory over some reasonably large, but not infinite, volume of de Sitter space. And then hopefully that will take care of the problem within that volume. But yes, if you really want to describe all the degrees of freedom of quantum field theory over very large volumes, there may be a problem.
Now, wouldn't that necessarily break this decision?
The operators?
Projection.
Sure. Yeah.
So, well, what have you solved it? I don't know.
Well, the idea would be that you would look at the global de Sitter solution. You would choose some region inside that space-time that you want to describe and where you want to reproduce effective field theory. And then in that region, you would find an appropriate set of operators.
Sure.
And that the set of operators would depend on where you want to study.
I thought we wanted to sit in Barney.
That wasn't my requirement, no.
Oh, fine.
I'm getting confused.
Yes.
Are you doing that in the XY space or in the Z space? You've introduced some relational coordinates in which the coordinates are really values of scalar fields, right?
Let's think of it as in the XY space.
But then you're not, this projection is not preserving local field theory within the space in which you wanted to preserve it in, right? Your causality properties are in the Z coordinates. Is that not correct?
I guess I don't. Okay. Let me just first of all say this was a somewhat vague proposal. It remains to be fleshed out in full detail. Okay. So I don't really have a whole lot to say about it. But I would also say that causality properties don't refer to coordinates. the causality properties I've discussed so far refer to some background space-time which has some causal structure. And yes, it will be true, it's very important, this is some horrible non-local thing to do to a field theory, this notion of projecting into a finite dimensional set of states.
Well,
so this will screw up the microcausality relations at some level. Okay?
Yeah, so causality is also an issue, I guess, that maybe it was asked while I had to be away. The coordinate system, when you're measuring causality, you're measuring it in those z coordinates, is that right? What sets the geometry of those z coordinates? How do I even figure out what causality
again,
is there?
What I was talking about here was in the context of some kind of semiclassical expansion, where there's some classical geometry with some fixed causal structure, which is specified in some coordinate-independent way. And then at every order in the semiclassical expansion, I will talk about microlocality relative to that classical causal structure.
So it's inherently perturbative.
My statement about microcausality is inherently perturbative, and I have no expectation that it holds in a non-perturbative sense.
We should give Don a chance to wrap up so people don't miss tea and cookie time.
All right. I don't really have anything more to say. I mostly wanted to say that, I just mostly want to say this is an interesting set of questions to study, and I think these are interesting operators to push forward in some of the ways which have been mentioned, but I completely agree that they are unlikely to describe interesting physics in truly generic states, which would either represent things that are in ADS, a black hole with a sort of thermal gas around it, or in de Sitter space, we might expect that a generic state looks essentially like empty de Sitter and doesn't have one of these coordinate systems thereof. Okay. Nevertheless, right, I guess I'll stop there. Thank you very much.
Any other pressing or quick questions?
What's your recommendation for invariantizing the scalar power spectrum of gravity?
I don't have a recommendation.
Anything else?
Yeah. Any questions?
I would say.
No, here, so you have in the quantum gravity sense, you have matrix contributing, which with respect to which the 2 points are not are basically time-like related.
When you're outside of perturbation theory, that will almost certainly be true in some sense. Full path integral has that.
This can be never a perturbative effect. It never shows up in perturbation theory.
I claim it never shows up in perturbation theory when you use these observables and when you ignore infrared issues.
Okay.
All right. Well, thanks again.